Hello everyone, welcome back. Today's video is on flowing water. The learning outcomes of today's video is to define a drainage basin. We're going to define different types of river flows, and then we're going to look into various fluvial processes. So water likes to go from areas of high energy to areas of low energy. And so it'll always flow downhill. And with the hydraulic cycle, we have a lot of movement of water and displacement of it, and rain will fall in the mountains, and then all that water will collect and run down into the ocean with gravity. And so there's two different types of water flow. You have sheet flow, which is a continuous film of water flowing over a given surface. This is very common in the environment because channel flow erosion processes happen. And as water rolls down the side of a hill, they will take sediment and bits of mass with it. Water loves to carry things. That's one of the very interesting properties of water, is that it can really carry and push sediment and boulders downstream. And that's going to etch out a channel over time, which is where the water is going to preferentially flow over the next pass, the next water event. These then collect from tiny rills, which is the name of these little tiny streams that you see maybe on your gravel driveway, or if you're ever on a trail and you just see like a very small, maybe 1 centimeter stream. That's called a rill. Those rills collect into small streams, and then those streams collect and merge into large rivers, forming this large branching pattern called a dendritic flow pattern across a drainage basin. And a drainage basin is an area of land formed by the natural flow of water. Every drop of rain that falls within this drainage basin is going to end up in the same place. If it falls outside of this zone, it's going to a different drainage basin, but it is the area defined by the flow of water. It captures all the precipitation in that region, and then it contributes that precipitation into a stream that eventually empties out into some larger body of water. This is the San Lorenzo River Basin, which is relatively small. It's kind of interesting. We live on this side of the mountains, and so the rain that falls on just specifically our side of the mountains doesn't go very long before it ends up in the ocean, which I think is really cool. Here are some really big drainage basins. You have the Pacific Drainage Basin, the Gulf Drainage Basin. Those are separated by something called the Continental Divide. Then you have regions that don't terminate at the ocean. These are areas called endorheic basins. And that's where river or water that falls in this basin, it's like captured like a bowl, and it ends up at some salt saline lake typically. So over here in Eurasia, we have it end at the Dead Sea or the Red Sea. In the Western United States, we have a small endorheic basin that ends at, does anyone know of a saline lake in the Western United States? It ends at the Great Salt Lake. So it sort of sits within this bowl that's been developed by the mountain ranges that surround it, which is pretty cool. So water that falls within that basin is never going to go to the ocean. It's going to end at a small saline lake. It'll pick up salt and things along the way, and then that will evaporate and then reprecipitate and participate in sort of its own hydrogeologic cycle. And so river flow is determined by the gradient of the slope of the topography. And so something with a really steep gradient, a steep slope, is going to have a swift, more rapid flowing stream. And that's because there is more potential energy. There is more energy turning into kinetic energy with that river flow as it slides down the side of that mountain. And then it's also determined by discharge. So the amount of water going through will tell you the velocity at which that water is proceeding. You can have a really small area and pass the same amount of water through it if it's going a lot faster. And so that is how you determine the type of river flow you expect in an area. All rivers have zones associated with them, and that's called the headwaters. You have sort of an intermediate transfer zone, and then you have a depositional zone. And so the headwaters typically have fast flowing water that is cutting through the sides of mountains. There's a lot of erosion happening because the water is moving so quickly. Sediment transport is a function of river velocity. So the faster a river flows, the more erosion is going to happen. And then as it gradually gets closer to its end of life, its sort of terminal and its delta, it's going to deposit, it's going to slow down, deposit that sediment, and make these wide regions called floodplains. And at these floodplains, it may split off again into different meandering streams and braid off into a river delta. And that just depends on how much sediment is being eroded from the headwaters, from the transfer zone, and then being deposited finally in zone number 3. So the steeper the slope is, the more sediment transport will be there. The more shallow slope, the more deposition or accretion. That's the word we use to describe the opposite of erosion is accretion. More accretion will happen in these depositional zones, and you're more likely to find a meandering stream. A braided stream is what we call this sort of braided weaving pattern of rivers within a flood region. And so your distance from the headwaters will also tell you what kind of sediment you're going to find in your stream. And so I'd like you to take a moment to think about why that may be. So like I said, river velocity increases at these headwaters. So we're over here, we're in our headwaters. That's when our water is moving the fastest because it has the steepest gradient. This is going to wash every type of sediment away except for really large boulders and cobbles. As you move away from the headwaters, the slope is going to become more gradual and your grain size is going to get a lot smaller. If you're not familiar, this is sort of the way we categorize different sediments. Boulders and cobbles are very large. Gravels are a little smaller. Sand is smaller than gravel. And then finally, we have silts and clays, which are really, really fine sediment particulates. And that will sort of sort itself. It's a depositional sorting based off of the typical stream velocity in that region. In our headwaters, it's a lot faster. It's able to take away almost all types of sediment and just leaves behind these big boulders and cobbles. And then as things slow down away from the headwaters in the depositional zone, that sediment will drop out and deposit in sorted deposits. There's just all silt in this region. There's a lot of sand in this other region because of the stream velocity in that area. And so here are the parts of a river. The thalweg is the deepest part of the river. It's also the region of the river that is going to be the fastest. And that's due to sort of the inertial flow of water. It's going to come around bends like this and keep going until the bank pushes it the other way. And so you can see there's sort of an asynchronous, out of sync sinusoidal function. You have water being directed by the stream bank and it's moving in the stream width at sort of a pace that is out of sync with the width. When you exit a point bar. Those are these regions that preclude and push into the river. The thalweg is going to be on the very opposite side of where that point bar is. And that's because of the tendency of water to just keep flowing until some force acts on it. And so this water wants to flow straight into the outer riverbank, and then that riverbank redirects it, and it then turns and does the same thing again. That also means that the water flowing near the point bar is moving really slowly. And like we talked about on this slide, water that's moving slowly is going to deposit sediments there. And that's when you develop a point bar that will even start stretching further and further into the stream area. This is going to direct the thalweg even further up into the other side and start eroding the edge that it's reaching into. So it really is very interesting how rivers change over short periods of time. You can come back to a river after a month and see erosion and accretion in practice. So here in this photo, as it's coming around this bend, we have our thalweg hitting this outer bank and then being redirected. And then on the inside bank, we have sediment depositing, accreting, because the river is flowing slower. So that's our point bar, and then our cut bank. It's being eroded, and so it's being cut away slowly over time. And here is an example of the Mississippi River. You can sort of see historically where there have been point bars and cut bars. And so over time, it will become so loopy and constrained that it'll actually cut through and make something called an oxbow lake. This is an oxbow lake. You can see here that it's even, those oxbow lakes have filled in with sediment. Farmers have set up in those areas because sediment is really high in nutrients. And so you can see how the hydrology, the flow of water has impacted the way that people are inhabiting it and using the space. And so I think this is really cool. It's kind of like scars on the landscape. It's still happening as the Mississippi is still flowing, but you can see where it used to flow millions of years ago, or even hundreds of years ago. And so when the United States was formed, there are some states that define their boundaries by rivers, and the natural movement of water and the erosion of sediment makes for some really interesting state boundaries as these rivers meander and cut things off into point bars and make oxbow lakes. So in review, we have our three zones: the headwaters, which is where things are moving at a higher velocity. They're moving, it's a lot steeper in the headwaters. The transfer zones are lower elevation, so that merge down into more gentle slopes. And then finally, we have our third zone, our depositional zone, our river deltas, and very gradual floodplains that are full of depositional sediment. That's where sediment is accreting, and it's causing all of these river characteristics to change along the way. Its discharge, its drag or friction, the type of sediment also impacts the flow of water over it. If you have big boulders, they're going to cause a lot more friction than smaller sediments. And so that also plays an impact on it, and the amount of erosion and deposition that you would find in that area of the river. And so finally, to wrap up here, I want to talk about fluvial processes. A fluvial environment is a river environment. There's a lot of Latin terms used to describe different environments. And so I'd like you to know that a fluvial environment is a river. It is a riverine environment. It is the region created by a river. Very important fluvial processes are erosion, transportation, and then finally deposition. And we will get on more into this next week, but the flow of the river dictates the amount of sediment that's eroded out. Then that sediment is transported and carried along some distance until finally it's accreted and deposited on the side of the stream. This is dependent on the speed, the size of the sediment that it's carrying, and then also water temperature and sediment density, which is typically a specific gravity of 2.6. That's its density. And I want you to think about why that is. And so here we can plot out a figure of different particle sizes and flow velocities and create a sort of region in which we'd expect which fluvial process is occurring. So pebbles, cobbles, and boulders need a really large flow velocity in order to be eroded. For most velocities, they're just going to stay there. They're not going to move at all. Fine clays, really fine particulates, are going to be transported with any amount of flowing water, and they'll just keep moving and transporting along the way. So it's easier to move lighter material, and so it's going to be easier to move smaller particle sizes at the same flow velocity. And so that wraps up our video today. Thank you so much, and please don't hesitate to reach out to me if you have any questions.